evidence was there because some referee asked that it be put there. So if you actually look at the paper, you know, you kind of know that this is not what they did. But of course, if you look at the press release, you have to read it very, very carefully to figure out that they didn't actually say they have a topological qubit. And so, of course, the way that it went through the media and the social media was that, whoa, they finally have a topological qubit. And yeah, so a little bit of the backstory is that Microsoft has been working on this for, I don't know, 10 years or whatever. So in 2017 and 2018, they published papers about the properties of their nanowires. This is how it works in practice. So you have these tiny little aluminum, I think, wires, and it's kind of a combination of a superconductor and a semiconductor, and then magic happens. So, you know, math does its thing.
But you see, why would she say that if she's a scientist? Or maybe she's mocking them? Like, I would expect more, like, scientific or rigor, like, going in detail. Anyway.
And there's supposed to be these topological modes in this tiny nanowire. And they've so far already had 2 retractions, one about the properties of their nanowire, and the other was a paper in 2018 in which they already claimed they had evidence for topological qubits. So understandably, like, the community is very, very skeptical of what's going on there.
Well, okay, it's one can be skeptical and one should be. In fact, there are a number of results we'll talk about in this episode that one should be skeptical about. But I think it's worthwhile elaborating a little bit on the potential utility and importance of what are called topological qubits. And I'll step back a little bit for people who don't know all the words sound mysterious, and just say briefly what they are and why some people are excited about them, or why everyone's excited about the possibility, at least, of using these. The idea is that, remember, a qubit is instead of particles, instead of being quantum particles, instead of having just ones or zeros, can be in some linear combination of those things. And we generally say that these particles don't have to be one; they can have some phase, some extra quantum property associated with them, and the phase represents the quantum characteristics, and that's what makes it a qubit. It doesn't have to be in one state or the other, but a superposition of those states. And a topological qubit. The problem, of course, the reason quantum mechanics is so confusing and difficult, is we don't experience it every day, and we don't experience it every day because quantum mechanical correlations and these phases get washed out in the classical world of you and I, and we don't see them. And so the real challenge to make a quantum computer is to make sure all the things that normally wash out quantum mechanics don't wash out these important quantum mechanical effects you actually want to measure. And the nice thing about what's called a topological qubit in principle is that it's not just involving a single particle, but it's a coherent superposition of lots of states in a detailed condensed matter system that together behave in a way which once again has a kind of weird phase associated with it, which you can use as a quantum mechanical property to define a qubit. And what makes those interesting in principle is, well, if you have noise, heat and noise, it can of course take a single particle and knock it out and change its configuration. But if this configuration is based on many particles and involves a property where to be changed, the whole system, the whole set of many particles has to change its configuration together, it's harder for noise to change that system. And so what makes topological qubits interesting is that it may help quantum computers counteract the major thing that gets in the way of quantum computers, which is noise and basically washing out of quantum mechanical correlations. So if they can do it, it may, I was going to say it can, but it may be very interesting. The reason I'd say may is it's something that I think I heard Sabina talk about elsewhere, which is important, which is it would be great to have a topological qubit. The question also is one of scalability. Can you create the system? These topological qubits are obviously hard to make. They've been working for a long time, and they're theoretically possible. If they've been able to do it, it's great. But can you do it in a way that controls the system so you don't have just one, but a million of them? and keep the temperature of the system low and everything else, that's also remains to be seen. But so I think the two takeaways, and Sabina, you can correct me if you think I'm wrong here, are one, what you just pointed out, which is they may not have even created them, and two, can the system is the system indeed scalable? You want to add to that at all?
Yeah, so you mentioned the number like with the 1 million qubit. This is like the typical estimate from all the other quantum computing types. I actually don't know how many qubits that'll be on a topological quantum computer, because my understanding is you don't need quite as much error correction. In theory, kind of, you still need to do it, but maybe not as much, so maybe you'll get away with a little less. But I'm not sure it matters all that much, because if you look at the image that came with the press release, there's someone who is holding a hand and it's holding this topological core or whatever that counts. So we know it's like some palm size. Like, this is like huge if you need to cool something to millikelvin also. And they say that this thing, if it were to work, would have 8 qubits. So that's certainly not going to get us anywhere. So, you know, we need some, like, you know, maybe 100,000 things. To millikelvin, it's very low. Helium, you still have to worry about noise to some extent. And so this is why these devices are so huge. Like if you've ever seen the footage or an image like Google from IBM, where these things that look like Challenger or something. That's the cooling system and the noise buffering and stuff like this. And then you have this chip, which is kind of, you know, this tiny thing at the very bottom.
Holy shit.
So now you have to somehow do this for 1 million chips, or, you know, let it be a few 100,000. That becomes very difficult, and this is why IBM and several other companies are now looking into actually connecting a different kind of fridges, and that just brings in more sources of noise and becomes more complicated. So this is the thing that I worry about, and if you know, if the topological qubits end up being so huge, you don't gain all that much, you know, because you can't put it on these chips. So I'm not super excited about it, honestly. If I look at the physical reality, like theoretically, it's a nice idea, but in practice, I don't know. I mean, the other thing maybe I should say is that, of course, Microsoft are the only people working on this. For one thing, Google has been looking into this a bit. They published a paper last year. Nokia seems to be working on topological quantum computing. I only found out about this like 8 years ago. And then, of course, there are, you know, various academic institutions. And this is where the biggest criticism comes from that I've seen. It comes from people who study this stuff in their laboratory, and they look at the data and they say, I don't think.
Well, it'll be interesting to see. I think that's the point. It'll be interesting because the research is certainly interesting. And as you pointed out, one of the advantages is if these systems, if they're more impervious to noise, then you need less error correction. Because that's what noise does. One of the reasons some of these systems use many qubits is for error correction. You want to have redundancy to get rid of errors. And if there's less impact of noise, you need fewer qubits, and that may be useful. So the point is, I think may 1,000 flowers bloom. We'll see what works, what doesn't. In any case, it's not around the corner, but it's interesting to see. I think it's important to explore many different possibilities, because this field is still in its infancy, and in spite of all the hype.
Yeah, maybe a final word, since you said it's not in the near future. So the press release said we can do it in years. I don't think so. Really.
Well, we'll see. Let's hope we're still around in years talking about this, and we'll see if we're right or wrong. Okay. Okay, I want to, I was going to say I want to come down to Earth, but not quite. I want to go out into space. I think it's appropriate because just this week, the first private company, first commercial lander landed on the moon. In fact, it's the first U.S. lander, I didn't realize, to land on the moon since 1972, since the last Apollo astronauts landed on the moon. The United States has not had a lander that landed on the moon. I didn't realize that. I was reading in a Nature article. But in any case, there's two. So there's a commercial lander that landed on the moon. There's another NASA object that's orbiting the moon. And the idea is for the one that's just landed near the south pole of the moon, and the one that's orbiting is to look for water. And the lander called Odysseus that's just landed will actually drill down into the soil. The argument is that there's water in the moon, it's probably stored near the poles, which don't get direct kind of sunlight, and therefore might harbor water more carefully. And the question, so it's very exciting. It's very nice that a lander has landed on the moon and successfully done it. They tried it a little while ago, but they landed it and then toppled over. So this time it stayed upright. And there's a nice picture that was sent of its shadow on the moon. But the thing you might ask is, okay, big deal. Why do we care if there's water on the moon? And I want to just say the two reasons I can think of. One is a practical reason. If we're going to use the moon for human activity and build a base on the moon, then obviously having water on the moon and not having to bring it with you is a very useful thing. And there's also been discussion in the long run about fueling the moon as a fueling station for rockets, which makes sense because it's a lot easier to escape the gravitational pull of the moon. And so if you have rocket fuel and you launch the moon, you need less fuel basically to escape and go like Mars or elsewhere. And if there's water, that's a great raw ingredient to help make rocket fuel. So from a practical perspective of technology and potentially human space exploration, it's useful. But from a scientific perspective, it's also very, very interesting because this water has been around since the early formation of the solar system. And one of the big questions, and it's still not fully understood, is where does the water supposed to come from? How is it stored in rock later on in deposits like comets and asteroids? And so we're interested in the early development of the solar system, which may be relevant for trying to understand, for example, how much water there was on Mars. If you're interested in life, potential life, or whether it was habitable at early times, is to know the history of water. So if you could measure this primordial water on the moon, you'd first of all be able to get an estimate of how much there was. Also, it's isotopic science will tell you about where it came from. And it's relevant to really understanding the evolution of not just the moon, but the Earth and potential formation of life in the solar system. So those are two reasons to go to the moon. And I will, once again, I can't forget anything else. What's really neat about it is they involve robots. They don't need people to do it. And I, once again, recognize that you can do so much with robots that it costs so much less. You didn't need people to go up there and dig for water on the moon. But either way, that mission will help us if you do want to send people to the moon, but maybe make it.
Yeah, well, the first thing I want to say is that there is landing footage from several cameras on the lander, which you can watch online. I recommend you do because it's great to watch. So the other thing is, I got a little confused. I thought already knew there's water on the moon. So if you say water on the moon, I have like this image, like some kind of infrared image where I think it was one of the Chinese
Yeah, looking at spectroscopy orbits have detected evidence, and it's that there is water located on the moon. That's right. But the idea of exploring exactly how much, what is isotopic abundance, obviously you have to go there and look.
Yeah, so when you say isotopic abundance, you're talking about the isotopes of the hydrogen.
Hold up, something. We're not done yet.
Yeah, yes. What hydrogen versus deuterium, for example.
Right. Yeah. So just for context, so since you were speaking of fuel, I think the idea is that you use the sunlight to split the water, and then you have hydrogen, and you can use that to, power your moon habitat, or blast the rocket into space, or whatever. Yeah. So you know, there are a lot of plans for building stations on the moon or for using it as an intermediate step to get to space, which would make a lot of sense because the gravity is less. So, you know, I'm pretty excited about it. Like, so, you know, let's put some stuff on the moon. It's also, like, the inspirational value is just super huge. You know, I see this in my children. You know, you can tell them, like, that this is the moon, and someone landed on the moon. Here are the images. Like, this is what it looks like. See, there's the dust, and there's the shadow, and so on.
Yeah, no, I think it is inspirational. And as I say, you don't always need people to be inspirational to get them on the moon. It's still, the moon, when it comes to human space exploration, the obvious place to build for explosive is the moon again, and try and see what you can do. You can learn a lot about how to build things and everything else. And so that's why it always amuses me that some people, unnamed, for some reason think going directly to Mars is the way to go. But I think rational people recognize that if you want to, baby steps, if you want to go into space and get humans working in space, the moon is right there, and we went there once. We really did, no matter what some people think. And knowing what's there to help us build some kind of human-occupied facility is very important, and I think is very useful and inspirational as well, and won't bankrupt the country as well to do.
But you know what, Musk said why he didn't want to go to the moon? He does have, you know, some thought in the moon landing project. It's because he said, well, if there's a world war, the Chinese are going to nuke the moon.
Wow.
Well, okay. I thought it was because I mean, and the other argument is that you can't terraform the moon. You know, when we're in the moon, we'll have to live in a pretty harsh environment, although it is closed. And but you know, some people, most of the science fiction, think that you can eventually turn Mars into a habitable environment, and therefore one that houses a separate civilization. That's largely science fiction, at least in the near term. It may be possible in principle, but it's not going to happen. I think that's one of the other arguments. He somehow has community. I still, this is aside, but I still never understand quite how anyone really thinks they're going to survive on Mars' surface for a long time without dying from radiation. But you have to build interesting objects on that surface. But anyway, that's Mars. I think the moon is very exciting, and what just happened, you can look up, as you say, you can tell your children, look up at that, and then look at the online, and we just sent something that landed there, and there's its shadow, and one day it's going to help maybe get some people back there, which I certainly don't oppose at all. Okay, good. Your turn.
Yeah, so my next topic is also about space, but a completely different angle. It's about how can we measure whether space has quantum fluctuations. You'll know that one of the biggest open problems in the foundations of physics is the question of how do we combine quantum physics with general relativity. Those two theories don't want to cooperate the way that they should, so we need a theory of quantum gravity. And there are various approaches to this theory, and we don't really know which one's the right one, if any of them. So a big open problem. So one of the most general expectations you can have of a theory of quantum gravity is that it would lead to quantum fluctuations of space. And that brings up the question, like, can you look for those? The answer is, in principle, yes. And so I was very interested in this kind of stuff like 15 years ago or something, and there were a few proposals that have been floating around. And so I just read, like last week, that one of those proposals is actually going somewhere, and they're actually going to build the thing. And it's basically, it's an interferometer, like LIGO, like a gravitational wave interferometer, just on a smaller scale. And they'll be doing single photon experiments, measurements, you know, where they look for deviations from the zero hypothesis, basically. So
Okay.
if there is any kind of noise, and we'll have to talk more about exactly what kind of noise, then they should see a signal. So they want to build like 2 interferometers, each with an arm length of, I think, 5 meters. And then they'll use the correlations between both to tell the signal from noise. Like, this is my vague understanding. I'm not much of an experimentalist, but I think that's the idea, basically. And so yeah, so that all sounds very good, but the devil's in the details, so to speak. So the issue is, if you just take like the vanilla expectation for quantum fluctuations in space-time, you can calculate what it would do to the propagation of light signals. It's in the literature, it's called light cone fluctuations, because you expect if space itself wiggles, then that can kind of deviate light a little bit. So it's a really tiny effect, but you would expect this to add up over long distances. And people have looked for it, they haven't found anything. So it's not so super surprising, because if you look at the most basic estimates, it's just the effect is just way too small, so we can't see it. Even if the light's traveled through the entire visible universe, giga light years or whatever, we wouldn't see it. So what this experiment looks for is a special type of noise that comes from a special theory that is based on Eric Verlinder's entropic gravity. I think he renamed it at some point, but I think this is like the name that people remember. And they called it the fluctuation geotropic, something with entropic and geometry. I think that's the idea. So yeah, when I look at the mathematics, I'm not convinced that this actually exists. It doesn't mean one shouldn't look for it, but I kind of, I'm not so super excited about it after having looked at exactly what happened. Oh yeah, maybe I should add, that was like 10 years ago, there was a very similar experiment at Fermi Lab. It was called the HoloLoop.
Yeah.
They also looked for some specific type of noise that had something to do with the holographic principle, hence the name, and we didn't find anything.
Yeah, they didn't. Well, look, I don't disagree. I think I will add some things. Experimentalists often look for theories because it motivates an experiment, and I understand that. And my feeling is experimentalists should do whatever they can do, and because theorists, nature usually is smarter than theorists, and so if you have a new technique and it might be useful, you don't always, it's easy to find something in the literature that you can disprove, and maybe you can. In this case, you're right, it's a special kind of fluctuation. The generic kind of, might expect quantum events are probably much from a quantum theory of gravity or much smaller. Nevertheless, it's incredibly important. Maybe I'll take away the word incredibly. It's very important for the foundations of physics to understand if gravity is a quantum. We have no reason to believe it isn't, but that's the frontier of trying to understand the fundamental nature of the universe. And so if we could have some experimental rather than theoretical handle on that, it would be very important. So I think any kind of experiment might be able to demonstrate the cosmic quantum nature of space-time. And the reason space-time would fluctuate in the quantum theory of gravity is the theory of space-time, and therefore if it's a quantum theory, the variables of that quantum theory are space and time, they become quantum mechanical and they fluctuate like quantum mechanical variables. So it is important to look wherever you can, as long as you can fund the experiment. What I found interesting about this experiment, and I've looked at it because I've been thinking about interferometers for a number of reasons, not to look at quantum gravity, but to look at some other things, and I'm quite interested in this experiment because I think it's going to, I might have predicted for something else, and we'll do it in another episode perhaps. But
Wow.
Well, I'm kind of a different way to look. I'm looking for a kind of dark matter, which I think may be interesting.
Oh, I see.
But what's important about this is it looks like it's a new technology. A standard interferometer wouldn't see this, but this uses why do they need reliable? You might ask. if you're looking at gravity. LIGO's arms that are 4 kilometers, this is 5 meters. And this idea of single photon counting is a new way, my understanding is a new way of trying to look at fluctuations in light. It may not be, it's not useful for gravitational waves, but it's a useful new tool to look at a quantum effect related to fluctuations in light. And that makes the experiment, from my point of view, interesting, because it's new technology. I suspect to be, well, I bet dollars and donuts they don't see the effect that they might be looking for. This new technology, ultra-sensitive techniques to look for fluctuations in light, my bet will find other applications. So
I should add, like, the major reason the experiment is that much smaller than LIGO is that they're looking in a different wavelength range. They're looking for much smaller wavelengths.
My understanding is that, but I also thought this idea of LIGO is looking at single photons and this other thing. So in any case, it's an experimental technique, and I haven't gone into enough detail to grasp all the experimental features that make it unique. But I think what makes this interesting is that it's potentially a new window, and it may not be a window on quantum gravity, but anytime you open a new window on the universe, from my point of view, it may be exciting because you might discover something you didn't expect, or you might find a technology that might be useful with elsewhere. And so I'm excited about seeing what happens. Although I think both you and I would be willing to bet a fair amount of money they're not going to see fluctuations that.
¿Por qué no lanzaste Carreer, bro? Ya nos estorba.
I think, like, we said a few times, like, any kind of experiment that controls something I think it's a little bit more complicated. It's always a question about focusing it in a high expensive. So
yeah,
like,
of course, exactly.
The risk benefit. Like, but this seems like, of course, when people, they don't actually have, costs. But just going by the size, it's probably not hugely expensive. And the holometer thing, I think it was something like 2 million. So now, if it was my own money, I would say 2 million is a lot of money. But for Formula, it's not a lot of money. So so long, as the experiments are fairly small, you can say, okay, let's just look. Is it good?
Yeah, sure. And I agree completely, and that's why I'm saying, if you can do it and you can afford it, go ahead. And 5 meters is the kind of thing you could do at a university, in a laboratory, at a university facility, or somewhere like that. And therefore, one expects it's going to be in the millions of dollars, not billions of dollars. And that's, again, you're right. If it's our money, it sounds like a lot. But when it comes to the kind of money that's needed to do forefront physics or forefront science in any field, it's the kind of money you need to spend. And it's a small fraction of what we spend on many other things. Okay. Well, I want to now literally go back down to Earth in different ways. There was a result that came out that one of the few optimistic bits of news related to climate change that I wanted to briefly mention. And I think it's important because when people talk about, the doom and gloom scenarios, the world's going to end with climate change, and I'm always against that anyway. No. But one of the potential long-term effects that could be serious for countries, especially Europe, which temperatures climate could change a lot, I think, is the claim that a very important ocean current, which is really the major mechanism of heat transfer and also salt and material transfer between layers of the ocean and around the ocean, something called the Atlantic Meridional Overturning Circulation, or AMOC. And what it does, it's a current that basically takes warmer water from the south and travels along the surface of the ocean and gets up to the north where it cools and sinks because colder water is heavier than warmer water. And then it goes back down to the south, and it's the major mechanism that transports heat and affects climate dramatically. And one of the claims that has been, one of the worries has been, with climate change, as you get polar melting from places like Greenland, as the water becomes both less salty and a lot of fresh water comes in, you might disrupt that current. And a number of calculations have suggested there might be a tipping point with enough melting, you might basically destroy that circulation. And of course, that would have disastrous effects, or at least have dramatic effects on changing the global climate, among other things. Well, the local climate as well in many places. And people have argued that sometime between 2050 and 2095, depending upon how much carbon we have in the atmosphere and how much heating and how much melting there is, it might, you might get to that tipping point. And anytime you have a tipping point, that's a real problem. Of course, these things are always speculative, but you've got to ask yourself, are you willing to risk it? And I think what's interesting is a new study that looked at 34 climate models in detail and looked under extreme circumstances, a 4-fold increase in carbon dioxide. I hope more than will actually happen, but we'll see before the end of the century. And also a great deal of massive freshwater melting. Even under those extreme conditions, these models suggested that the current would weaken, but not disappear at all. It's more robust than you might have imagined. And that's heartening, especially in these times where, as we pointed out, my country's, or not my country because I live in Canada now, but the United States is showing no signs of trying to reduce carbon. So as we think about mediating rather than combating climate change, perhaps, it's nice to know that possibly this disastrous effect won't happen. Now, the authors point out, of course, that you can't say anything with certainty, but they're confident, and other people, I think it's impressive work. So it suggests that we may be, at least that one significant concern may be slightly less important. So I thought I'd throw that out and hear your comments.
Well, I'd say let's wait 1 or 2 months, and there'll be a study saying exactly the opposite. So, so in the past year, or in the past 2 years actually, there have been multiple studies that said the risk is actually higher than we thought. So there's kind of a longer backstory, which is that the most recent IPCC report from the working group, whatever, I think it was from 2022 or something, said that the risk is low, or something.
Yeah.
Whatever. I can't really remember the exact quote. So don't worry too much about it. It was like the message. But then after this report, there were multiple studies about new measurements, whatever. They did some analysis, and they arrived at the conclusion, actually, it could happen within this century, and it's not as far-fetched as we thought it is. And they've also done more precise projections of what would happen, what would actually happen in Europe if the circulation stops. And it's a little bit, there isn't one answer because it depends strongly on where you are. It's basically that the north would get colder and the south would get warmer. It just so happens that Germany is in the middle. So, it kind of interesting. So in Germany, it would probably kind of average out with the global temperature increase. But this is like just the annual average. So we would probably see a lot of extremes into both directions. So basically, it would be very unpleasant. It would be a mess. So I'm not super sure that I trust any of these climate models to get the ocean circulations right, because my understanding is like the Atlantic meridional overturning circulation isn't one thing, like it's not one one loop, but it's a lot of different loops. They go all over the place, and no one really knows because there are only so many measurements we have about what's going on at the bottom of the Atlantic Ocean. So it seems to me all a little bit far-fetched, which is why I'm saying, by no means do I want to question that they did something wrong in the paper. Of course not. But I'm not sure how reliable these models are when it comes to something that we know that little about.
Well, that's a good point. I was impressed that they used 34 different models, which at least... and that they looked at extreme conditions. I guess my point here is I think it surprised me that it appeared to be more robust than than my expectations would have been. I think when it comes to this issue, I think you really hit the nail on the head here. We don't know. You're right. It's a new result, and there are other results that were different before, and one hopes that as we go on in time, we improve our estimates. We make the models more complex and we incorporate more features, and the predictions are both more robust and more accurate. Time will tell. And once again, I come back to, I think, what we talked about last time. The ultimate question comes down to how lucky you think you are, punk, as Clint Eastwood used to say. If there were a tipping point, it would have dramatic effects. Again, it's not going to end life on Earth. It's going to make life very different in certain places. Worse in some places, potentially better in others. But it's going to affect the global infrastructure and economy of many countries. And so we have to ask ourselves, are we worried about it? If this effect is possible this century, should we be thinking about dealing with it and thinking about doing what we can to minimize it? And I think the point you made here is a good one. If there remains uncertainty, and I guess we should argue that there still does, we might want to err on the side of conservatism in terms of how we behave in society and produce carbon. I think that's one of the lessons we have to draw.
So you just confused me again.
That's good. Well, I work it done. No, so far.
Well, you said like if there were a tipping point. Like my understanding is that no one actually doubts, at least no one that I've heard from, that there is a tipping point. Because
I guess
it's happened in the past. Like
no, that's right. I'm not. You're right. I thank you. I said misstated. If the tipping point is accessible in this century, given the kind of things we're doing, then that's what I really mean. You're right. There is certainly the point. Ocean currents change in the past. Greenland is completely melted in the past. All the things that people talk about as possible in the long term have happened in the past, and so people should not. One of the big problems. Talking about climate change, just like evolution, is people presume the world has always been like it is. And it certainly has been a lot different in the past, and it will be different in the future. Part of that difference will not be related to humans, but what is remarkable is that humans are the difference, something that many people still don't buy, but it's true whether you like it or not.
Yeah, the thing that worries me about this tipping point is, so we can debate back and forth how large the risk is that we're going to cross it with, whether we're year 2050 or something, but let's just imagine it happens. So after this, it doesn't really matter for Europe what we're going to pump out into the air, because it's already happened. Right, so it's not going to go away, at least not within the next 1,000 years or something.
Yeah.
So it totally removes the incentive to get anything done in terms of energy transition or something. So and that'll screw over the ambition for the rest of the world. So it's my feeling is that if we cross this tipping point, that's the end of climate. Basically, maybe I'm overly negative, but
That's the end of what?
the end of climate action. Like, so if Europe doesn't pull their weight, I don't think that North America is going to do it either, and you can forget about China. And,
Yeah, well, I'm still waiting for climate action to start. So anyway.
yeah. Well,
Again.
you would have hoped that by 2050 something would have happened. Yeah.
Yeah, well, one would hope many things, but recent events have led me to wonder. Anyway, enough politics. I know people are getting into politics, but okay, let me go back to you then, Sabina, for the last item that you might introduce today.
Yeah, so my third item is the Google AI co-scientist, which, so I like the name. It's kind of like a Trojan horse, you might say, right? Yeah. Pretend it's harmless, but once it's in there, it's going to take over. It's not publicly available, but so the Google AI group has done a study with some select participants, and they've tried out this AI co-science, which they call a super agent. So the super agent is kind of the supervisor of 6 not so super agents, and each of these agents they all have different tasks. So the purpose of the whole thing is to help the scientists find a good research topic, like the hypothesis, a drug proposal, that sort of thing. So, I think it makes a lot of sense that AI might be helpful in it, because a lot of this comes down to literature analysis. Like, so you have to read and digest a huge amount of papers. You have to figure out what's already been done, what might be the next promising thing to do, how reasonable is this, and so on and so forth. And basically, this is what the AI co-scientists can do for you. And they had, so one of the case reports which they had, I thought was really remarkable. So they had a group and they did something with antimicrobial resistance, so not a but so they did some studies about this already in 2023 or whatever, and the AI proposed the next hypothesis for the test, and it turned out that they had themselves come up with this hypothesis earlier and had actually already done the study, and what the AI thought they would find was actually correct. So it was an unpublished paper, and so I find this quite remarkable. And so this is in biology, but I think that something like this could also be super useful in the debate, because my sense is that there are a lot of connections between different research areas that we're not making because people are too over-specialized. It's like the entire literature in foundation systems is just too large. So it makes a lot of sense to say, let's just feed all this stuff into an AI and see if it finds any connections that we hadn't thought of. And so I think that there's a lot of potential in that which we're currently just not using.
Well, okay, that's fascinating. I think, let me comment, I guess, I think it's funny because when I knew you were going to talk about this, I wrote down the word literature search for myself, because when people talk about a co-scientist, and I think I saw a tweet by you today about something that, you know, that's within a certain amount of time, very soon, next year, AI would be doing new physics itself, and you said if it does, it'd be wrong. But more importantly, I think people get the sense that AI is going to take over for all the scientists. But what AI is really good at right now is literature. Basically, what AI does is take a lot of information and search through it. That's really what AI does. and it does it, and it can do that much more effectively than humans. It can go through vast amounts of situations. If you're driving a car, it can go through vast amounts of situations, what different things look like, and decide if you're hitting a pedestrian or whether a leaf is blowing across the street. And so where this will be very, very useful, literature, which may unfortunately be bad news for graduate students, because I think I remember a friend of mine, who won the Nobel Prize, said, what's great is that graduate students, in principle, be out there to learn everything, and then you download what they learned so they do the literature listening, and you decide what's interesting. And so it may be bad for graduate students, because you could probably use AI more effectively to search the literature if you wanted to decide what might be an interesting research topic. Absolutely. And I think what you said is absolutely true, that where being able to distill vast amounts of information to decide what may already be known, what may be interesting, what isn't known, is the kind of thing you want to use for a human scientist to decide what's the next interesting project to work on, or what might likely be useful. So that's in the sense in which this co-scientist would be very useful. It wouldn't be a scientist, but so I think it's potentially very useful, but not revolutionary. But one of the areas where I've always thought AI could impact very usefully on the project. I'm intrigued by you say I'm left more sanguine. Well, I'm less optimistic that AI will help. I suspect the real problem with the foundations of physics is not. I'm more skeptical. It's not big connections between what's already known, but probably things we haven't thought of yet. And so I suspect this will be more useful in an area like biology, where there's so much going on, so many different experiments, so many results. The field is changing by leaps and bounds, and it's probably very difficult for individual scientists to get a handle on things. I would love if I were wrong, if there were some connections between things that are known in fundamental science that might lead us to new results. I suspect most of what's being done is wrong in fundamental science, and that we probably need some new ideas, and I don't think the individual scientists will help with that. But again, I can have to be wrong.
Well, so I don't know exactly. It just seems to be like it's the obvious thing you want to look for. But I can tell you from my own experience that like an area where it might actually work is the intersection between astrophysics, dark matter studies, and condensed matter. Because if you remember, like we talked about this a long time ago, that I've been working on this idea that dark matter is some kind of superfluid. And that gets very deep into the condensed matter stuff very quickly, which I don't know a lot about. So I was like very quick, I had no idea what are we actually talking about. And I had some effort to figure out what these superfluids actually do under gravity. Like, and it turns out that this is actually quite an interesting question. Because, the people who study superfluids in the laboratory, they have no need to look for inhomogeneous, gravitational fields. They just use a gradient. So what does the thing do in the gravitational field of the galaxy? Well, people made some approximations, and so, so I think that, there are probably some connections there. Yeah. But what we don't know them, because there aren't remotely sufficiently many people who know about astrophysics, about galaxies, and about superfluids. So this is like an example where I think it could be useful. But let me add another thing. You seem to agree that it's useful for literature analysis and stuff like this. I think that's the second point where even the current AIs are useful, which is they can generate random ideas and discard them much faster than we. So they can basically scan a larger possible space of hypotheses, within the snap of a finger that would take us a year or something.
Yeah, and see what's not what we're already known about and I have to say already, in my lifetime, the changes. It used to be, when you were working on something, you used to have to go to the library try and figure out, and it would take you weeks maybe, to see what papers were written, find the Internet library, find if that journal was stolen, you know, or existed and you had to order it from some other university, and find out what was known. And then the Internet changed that and made it so much easier for us, for anyone, to do that kind of work. And this could be the next step in the next sort of evolution of that, where it becomes easier and easier to basically find out what's known and what's not known. And that can't help but be useful. So I think it's and where, you know, how useful, well, we'll see. But it's certainly one of those areas where, unlike some of the claims about AI, AI can be a very useful addition to something. And as you point out, it already has been in certain ways.
You know, a lot of those AI people have a fascination with solving physics. So I made a video about this like half a year ago where I had a couple of quotes from those people, and there are like, linear, we're going to solve physics, we're going to fix quantum gravity, or whatever. So I find it kind of interesting. Like, it's like they're envious physics or something. So they want to come for us.
Well, physics engine, yes. Although committee decided AI was useful for physics this last year. But anyway, okay, now I'll go from Earth to the stars. The last item I went through, before we have a general discussion about something else for a few minutes, is a really interesting potential discovery which claims to have been discovered many times before, which has led one cause. But the James Webb Space Telescope, which after all is designed to look back as far as the back to the generation of stars, ones with the claim that they've seen something which we've been predicted for maybe 100 years, not quite, but close, 80 or 90 years. And that is the first generation of stars. In the early universe, the only elements that were around were hydrogen and helium, to a very tiny bit of lithium, but not the other elements. I always loved it when astronomers call them metals and heavy elements. You know, we're talking about everything than helium. But obviously, to make you and I, we need more than helium and hydrogen. And our sun has a lot of it and other elements, and so does the solar system. And then those elements had to have been made inside stars. But the first generation of stars, therefore, would have just involved gas collapsing, which was just hydrogen and helium. And those kind of stars are very, very different than the stars we see now, because one of the ways a star can cool is by interaction with fusions of the heavier elements, which allow energy to be dissipated by radiative transitions and all that sort of stuff. And so the early generation of stars would tend to be very, very big, because it would take them, they keep collapsing slowly until the system was big enough to be able to allow it to cool by other mechanisms or to initiate fusion. And so the earliest the typical astronomical nomenclature is exactly wrong. Those are top 3 stars. The oldest population is the top 1, but astronomers do most things backwards. The population 3 stars. It's been populated, well, we know population 3 stars would have formed. The question is, when would they have formed, how easily would they have formed, and what would be their impact? For example, 100 or 1,000 solar mass star, which wouldn't exist now, or 1,000 solar mass star would burn, but even 100 solar mass star would burn so fast compared to the sun that it would then go supernova and start generating other heavier elements. And it might also be relevant to understanding, therefore, the next generation of stars, but also the formation of galaxies. These hot stars would burn very hot in the ultraviolet, and ionized interstellar medium, and it would change that as well. And it may also be relevant to understanding the first formation of black holes, large black holes, because if you have 100 of those 1,000 solar mass objects that then coalesce, you might explain why you get large alien solar mass or large black holes.
Fucking
It's a very important subject.
Target my mark!
And recently, some analysis of the James Webb Space Telescope has suggested that while if you're looking at individual galaxies, it's going to take an incredible amount of time to have the spectroscopic sensitivity to look for these populations of these stars. What they're doing, I suppose, is basically look at hundreds of thousands of galaxies and just look for signals where the hydrogen line was strong, but you didn't see, say, an oxygen line. And so you buy it, and based on that search of 100,000 galaxies, they found 2 galaxies, one of which was a very good candidate, 850 million years after Big Bang. It's called GLIMPSE, GLIMPSE-16043. It's a galaxy which just has 100,000 solar masses, which means it's a dwarf galaxy, an early galaxy. Our galaxy, to remind you, has 10 billion solar masses. Or, yeah, well, 10 or 100 billion solar masses, I should say. 100 billion. This is just 100,000, an early galaxy, and they see some evidence for what they would say is some top 3 stars. It'd be very important result if it's true, because it'll begin to tell us about all of those issues: ionization, interstellar medium, the first stars forming, heavy elements forming, black holes, all sorts of stuff. Because after all, we are the children of the first, even in our galaxy, we are the children of the top 3 stars. So if we want to learn about our own origins, it's important to know about them. It's fascinating, it's true. The only thing I'll say is at least 5 times that I know of in the last 10 years, these things have been discovered. And so I'll take a wait and see approach. And I'll throw it back to you.
Yeah, so honestly, I don't know a lot about this. So you said that it's like 850 million years after the Big Bang.
Yeah.
So I'm terrible with these numbers. Do you remember what redshift this is?
Oh, it's, redshifts of, 13 or something like that.
Yeah, right.
It's, I mean, the oldest galaxies seen are now claimed to be 250 to 300 million years after the Big Bang, which is, you expect hundreds of millions of years for galaxies to form. So the oldest stars should be around that time. It's just hard to see them, and I think a lot of people have thought it would take a lot longer. That's what the James Webb Space Telescope, one of the things it's designed to do, is look for these old stars. And this would be what I think is exciting about the results. It's true is that this quick and dirty technique of just roughly scanning has then given you, well, it's almost like AI, doing a literature search. This is a quick scan of 100,000 galaxies, looking for something that may be potential, and then zooming in on it. And that's what they claim to have done. And if they did, this would be the first unambiguous measurement of the first generation of stars that formed in the universe, which are the precursors of everything we see in the universe today. So I think that would be very exciting.
Yeah, certainly. When you said this, I felt like, I think I've heard this before. It's been claimed a few times before. This explains why I was confused about the time. But the other thing that I remember reading is that these first stars were kind of too early. Like they were earlier than they should have been according to I don't know what.
Yeah. There are some claims that we see too many stars, too much structure early on, and some people say, the Big Bang's wrong. But the point is that, star formation is complicated, galaxy formation is complicated, and naive estimates, if they're off by a factor of 2, it's not too surprising when you come to the details of complicated systems of gas. So yeah, some people have argued we see more early galaxies and stars than you might have predicted, but there's all these biases of selection and everything else. It's not worth writing home about, and I don't think yet even worth having a what's new in science discussion about at this point. But this is one thing that we know must happen. The first stars must have formed, and they would have all been top 3 stars because there was no heavy elements. And how they form and when they form and where they form, how quickly, how abundantly is relevant to almost every other interesting question in astrophysics and in cosmology. So since I believe data is a lot more useful than theory when it comes to trying to understand these complicated systems, it's nice if this might be the first observation that really is true. So I think it remains to be seen. But one thing is for certain, I think, this is the right place to use it. The James Webb Space Telescope is the device to look for this, because that's what it's designed to do.
Yeah, I also think, on a more spiritual level almost, it's also a good reminder that our sun is quite a newcomer.
Yes.
So stars have been around for a long time. There must have been a second generation somewhere in between number 1 and 3, right?
I think people would argue there's probably been our son isn't number 2 or 3, might be 10th generation. I think there's probably a lot of cycling going through before you can get the elemental abundance that gets our son. So our son is definitely a newcomer. Remember, our galaxy is about 12 billion years old, and our sun is 4.5 billion years old. And that's probably an interesting thing, because a lot of people say, well, there's different civilizations that could be 5 billion years older than ours. But the question is, well, if there aren't any heavy elements, do you have a civilization made of hydrogen and helium? Probably not.
Well, not from the first generation, what do you say, the third generation or whatever, stars. But certainly we would think like within the past, I don't know, 10 billion years or something, it should have been possible. Like, so, and forget about billions, like even if it's like 100 millions, if you have a civilization that has had 100 million years more time to grow brains or whatever, they're going to be so far, you know, above and beyond everything we can even think of. I don't know, maybe they're actually here and we just have no idea what we're doing.
Oh, don't say that. Now, well, no, I don't want to have that, because we'll get a lot of, they're not. Okay. We can talk about aliens in another episode. I think my estimate is, if there was extremely advanced civilizations, and there may be ones that survive. If you look at our own, it's not so obvious that they get past this stage. They're probably they're probably looking inward more than outward. There's nothing they need to know about us or anything that we have, and so they probably have no interest in I see no great reason why. It's probably they want to be left alone, and so.
I agree with this. It's like most of us can't be bothered to figure out how many species of ants there are in the savannah or something like that.
Exactly. Yeah, exactly. Anyway, speaking of what may be interesting or not, I want to end. Thank you. This has been fun. I like this format, and it's been fun. I hope we'll find out some comments if other people agree. But I think it's probably worth mentioning, ending with, you produced a video which sort of became viral, at least there were a lot of comments, about particle physics and hyperbolic planes. And I want to hone in on one, because I think it's probably interpreted. But I think we also might have slightly different perspectives on it. And that is, so where the only big particle physics experiment that's happening in the United States that's expensive, that I know of, is a big experiment at Fermilab to use a neutrino beam that will go underground and be detected at the Sedan mine in South Dakota. And one might ask, why are we doing that? And the idea is to send neutrinos be detected to look for the properties of neutrinos, and one property in particular is to look for what's called CP violation in the neutrino sector. To look for somehow a slight difference between neutrinos and antineutrinos. And that may sound like such an esoteric thing that you might ask, why waste your time doing it? And a number of people, and myself included, would argue that it's a very interesting thing to know. And I wanted to, and you made a statement about basically, I'll let you say the statement what, but it's to the effect of, too often it's claimed that when we do that experiment, we'll know how the universe originated, and we're not going to originated. And so why don't you elaborate on your concern about these hyperbolic statements, and then I'll talk about why I think and later why we both agree is at least might be, or at least why.
Yeah, right. So this is really a new thing. I've probably said the same thing, like 20 times in the past 2 years or something. But
this is not on.
Yeah. Sometimes it happens. So the reason it annoys me is that physicists make up these big claims about what this experiment is going to tell us. Like it's going to explain why we are here, or why the universe exists, or why we exist, and stuff like this. And
Woo,
you
see
know,
that?
you don't even need to know a terrible lot about particle physics to figure out that that's not going to happen. Like, and so I wonder, like, in 10 years or something, you can will have run, they will have collected their data that say, okay, what we found is like a CP violation. How do they measure it? With some kind of angle, right? So the angle is whatever, I don't know, 13 degrees. And so how does this explain why we exist? Right?
Yeah, no.
So what are they going to say? So I just think that like this is like false advertising. You know, they should try it a bit harder. So if they want to measure CP violation in the industry, it's like, okay, then tell people that this is what you're going to measure and why you're interested in it, but don't make up some nonsense about the existence of the universe.
Well, yeah, I think, look, I'm sympathetic to that. I'm older than you again, and I remember how many
Do you
things
remember
canceled.
writing a book titled
Yeah.
Universe from Nothing?
No, I definitely have written a lot of books. No, that's not what I'm saying. I remember many canceled projects. And the question is always one, if it's expensive, of trying to convince not just the public, but legislators to spend money. And sometimes, unless you make great claims, people will say, why bother doing it? So I think the particle physics community